In the last lecture, we talked about correlation, and we looked at correlation coefficients to determine if the correlation between two variables is significant. So in this lecture, we're going to assume that it is significant, okay? We're going to act like we tested, we did the test, we went through the hypothesis test, we found that that the two sets of data were correlated and that it was a linear correlation, okay? So now that we found this, what can we do with it? What's the point? So what we can do is we can draw a line that most closely models that data. And why would we do this? The purpose of doing this is that we can then predict what the y value would be given a specific x value that might not have been in our sample, okay? So what we do is in order to determine if there's a correlation, right, we take a sample, this random sample of x values, we determine what the y values are, and then from there we can run the hypothesis test, okay? Or we can use the critical values, that Pearson critical value chart. And now what we can do is now we determine that they're significantly correlated. Now we can start using this to make predictions, okay? So let's talk about what these lines look like, and then we're going to talk about how to find them. So a regression line it most closely models the relationship between an explanatory variable. Remember, the explanatory variable is the independent variable. And a response variable. This is your x, this is your y. Okay. We can use this line to predict y values for x values that are not part of the data set. I'm going to do this in a different color because just to give you a kind of a definition, the points that are on the line I don't want to say points, the y values of the points. The y values of the points that are on the line are called the predicted y values. And the y values in the data set, so these are from our sample. Those are the observed y values. Okay, so before we go further, let's just show you what a regression line might look like. So if you have a set of data, you have a scatter plot, and let's say that our scatter plot looks as follows. Okay, here's your data. Those are all of your data points. Your regression line might look like this. Okay, so here's your scatter plot. And here's your regression line. Okay, so to give you a better picture, because this is much clearer, here are your different points. These points are the ones from your sample. Okay, and this is what an outlier would look like. It would be way off of that line. Okay, these are the points from the sample. Then you have your line, and you'll see that this is called a trend line. That's another name for it. It's also called a line of best fit. Okay, and what we're doing is we're saying that the points, the y values that you see of these points would be called the observed y values. But the y values of any point that's along the line is a predicted y value. And you can see that some of your points from the sample fall on the line. That won't always happen, okay? Sometimes the line just won't pass through any of the points. That's because it's a best fit line. So what does that mean? What are we trying to do, okay? So first of all, let me go back to this for a second, actually. The difference between the y values is called a residual. So here the residual would be 0. Here we would have a negative residual because the y value at this x value, okay, is greater than the predicted y value is greater than the observed. The observed is below. So think of positive and negative as direction. If your observed y value is below your best fit line, okay, then you're going to have a negative residual. If it's above your best fit line, like all of these, you're going to have a positive residual. So the residual is the difference between the y values. Okay, so let's write that down. And the residual we represent with the letter D. So we calculate it by doing the observed y value minus the predicted y value. So then we have to talk about how do we actually come up with this line, right? We need an equation for the line. So the regression line, or the line of best fit as we define it, is the sum of the squares of the residuals has to be as small as possible, so as close to 0 as possible. So in other words, if we take all of these distances here, this distance here, this distance here, this distance here, this distance here, even the distance with the outliers, okay? The distance from the y value to the point, the y value of our point to the y value of our line, if we take the sum of the squares, okay, we want it to be as small as possible. Think of it kind of like standard deviation, okay? You want the standard deviation from the line, the deviation from the line, to be as small as possible. So the regression line, or best fit line, it's really like line of best fit. Is the line for which the sum of the squares of the residuals is as small as possible. You want the distance from the points to the lines to be very small, okay? Okay, so let's talk about the actual equation of the line. So the regression line is in the form y equals mx plus b. Now hopefully you're all familiar with this. This is the slope-intercept form of a line. Okay, m is equal to the slope, and b is equal to our y-intercept. Okay, let's just take an example. If we take an example of a line like 2x plus 1, okay, you can see here that the y-intercept is 1. And the slope is 2. That's because for every value of x that we go over, so we go to the right by 1, we're going up 2 on the y, okay? If we go here and we go to the right by 1, we're going up 2 on the y. If I made this negative, then we're saying change the direction of the slope, and now every time that you go to the right by 1, you're going to go down by 2. But our y-intercept is still the same. If we created a line negative 3x plus 4, okay, you can see here that the y-intercept is 4, and every time that we go to the right by 1, we go down 3, okay? So a negative slope means that as you go to the right, you go down. Notice that this is like the scatter plot where we said as x increases, y is actually decreasing. If we made this a positive slope, then we're saying, okay, well, as x increases, y also increases, okay? And here, it's a positive slope. So as we go to the right by 1, we're going up by 3. Okay, so you see the negative slope. When we go to the right, we go down, and the positive slope, when we go to the right, we go up. So that's the format of our line. Okay, y equals mx plus b. So the equation of the regression line not surprisingly, we use y hat to indicate that it's a regression line. And you're going to love this. Our slope is very similar to what we use for the correlation coefficient. Okay, so it's very similar to our R. It's n times the sum of x times y. So you take all of your x values, each x value you multiply it by its corresponding y value, and then you take the sum of that, minus the sum of our x's times the sum of our y's, divided by n times the sum of your squares for the x. So you take each of your x values, you square them, and then you add it all together. And then minus the sum of x squared. And then our b, our y-intercept, is y bar minus mx bar. So remember what y bar means. Y bar is the average of our y values. So it's the sum of the y values over the number of y values, minus m, and then the average of our x values. So the sum of the x values over the number of x values. So this right here is the average of our y values, or the mean if we're being exact about it. And this here is the mean of the x values. Okay, and just as a note, the regression line is always going to pass through the point that represents the mean of the x, comma, the mean of the y. That's always going to be the case. Okay. So what we're going to do, and we're going to do 2 examples so you get accustomed to it, okay? We're going to find the regression line, and then we're also going to find the residuals and use the regression line to also make predictions about other x values, okay? So we used an example in the last lesson where we figured out whether there was a correlation. So we had 2 examples. In one there was the negative correlation, in the other one there was no correlation. So we only do regression lines when we're talking about the fact that there's a significant linear correlation. If there's no correlation, there's no point in doing a regression line, because what we're doing is we're saying we really can't predict what the y value should be given any x value. There is no relationship, okay? So here, in the first example, we did have a relationship. So the first example was the number of years out of school So we're going to find the regression line. We're going to find the residuals for all our x values. Just again, so that you get accustomed to doing it. And then we're also going to predict y values for x values not in the sample. And as we go through an example, I think you're going to understand what all of this means even better. Okay. So in the previous lecture, we discussed the correlation between the number of years out of school and the amount of money they contributed to that school. In thousands of dollars. Sorry, I've been hiding this from you. I didn't realize that. Okay, so in order to find a regression line, you have to have the data. So I'm going to rewrite the data for you here, and then we're going to do all of our calculations. Okay, so we had number of years out of school. This was our x. It was our dependent variable. Our independent variable. And then we had the annual contribution, which was our dependent variable. The annual contribution changed based on the number of years that somebody was out of school. So we had 1 year, $12.5 thousand. Somebody was out of school for 10 years, $8.7 thousand. If they were out of school for 5 years, $14.6 thousand. For 15 years, $5.2 thousand. 3 years, $9.9 thousand. 24 years, $3.1 thousand. And 30 years, $2.7 thousand. Now keep in mind what a negative correlation means. What the negative correlation means is that as the number of years out of school increases, the annual contribution actually decreases, okay? Which may be a little surprising even, because you would think that the more years out of school, the more money you would have to donate, because a lot of times the amount of money that you have increases. You have a steady job at that point, hopefully, and you have paid off most of your loans. But that's actually not true. And you could think about, well, maybe why isn't that true? Maybe the less years you're out of school, the closer you feel to that school, you have a bigger bond. Whereas if you have been out of school for 20 years, you kind of forget where you went to college. Okay. It's not that important to you anymore. You have so many other parts of your life that you're involved in. Okay. So this had a negative correlation, and we could kind of see that, right? 30 years, it's only $2,700. 1 year, it's $12,500. Okay. Now keep in mind that doesn't mean that 1 year is always going to give you the most, right? In this sample, 5 years gave you the highest contribution. It's just that it's a trend. Okay. It's a trend. So let's figure out the line of regression. We're going to need to figure out the same calculations that we did for the correlation coefficient. The only thing that we don't need for this one that we did for the correlation coefficient was the sum of the squares for the y values. We don't need this for that, okay? So we're going to find the sum of x times y. That was in our formula. So what we're doing is we're working through that formula in pieces. We're saying, okay, I need the sum of x, y. Then we're going to take the sum of our x's, the sum of our y's, and the sum of our x squared. Okay, so we don't need the sum of the y squared, but we need all of these other numbers. So we have to calculate those things. And this is very tedious. There is technology that will allow you to do this. If I were to do this, I would typically use Excel. Okay, so there are calculators, certain statistics calculators that allow you to do this. That allows it to go a lot faster because this is tedious calculations, right? But what we would be doing here is 1 times 12.5 plus 10, so that's our next x value. The corresponding y is 8.7 plus 5 times corresponding y value is 14.6 plus 15, corresponding y value is 5.2 plus 3, corresponding y value is 9.9, plus 24 times 3.1, plus 30 times 2.7. So we're taking these values, the x and the y, we're multiplying them, and then we're adding that all together. So when we do that, we get 435.6. And following the formula, because you went through this lesson on correlation coefficients and how to calculate that, I would encourage you to pause the video and try and do the rest yourself and see what happens, okay? So then we find the sum of the x, and that just means take each of your x values and add them together. That gives you 88. We're going to do the same thing for the y. So 12.5 plus 8.7 plus 14.6 plus 5.2 plus 9.9 plus 3.1 plus 2.7, and we get 56.7 here. And then finally we have to take the sum of each of the x values squared. So that means that we're doing 1 squared, or 1, plus 10 squared, or 100, plus 5 squared, plus 15 squared, plus 3 squared, plus 24 squared, plus 30 squared. And that gives us 1,836. Okay, in the residual, we also would have had to calculate the sum of the y squares, but we don't have to do that here, so we won't. We also need to know our n. So remember, our n is the number of pairs or the number of x values. So that's 7. There are 7 pairs here. Okay. Okay. So let's take a look at the slope. So now we just plug in. So I'm gonna rewrite it over here. It's n times sigma xy minus sigma x, remember sigma is sum, sigma y over n times sigma x squared minus sigma x squared. Well, our m is 7. Our sigma xy we get from here. It's 435.6. Then we subtract our sigma x, that's 88. Our sigma y is 56.7. And then we have 7 again. Then we have our sigma x squared. So sigma x squared is 1,836 minus, and then we have sigma x squared. So most calculators follow order of operations. So I usually do the numerator first, then the denominator, and then divide. So what you get here is negative 1,940.4 over 5,108. And that gives you a slope of negative 0.38. Now I want you to think about this. It is a negative correlation, okay? If you remember, our correlation coefficient was negative, okay? Negative correlation. And what that means is that as x increases, y is going to decrease. Wrong window. As x increases, y is going to decrease. When does that happen? That happens when we have a negative slope. X increases, y decreases. Let me make this a negative x. And we'll make it just a +4 so that you could see it more clearly. As x increases, y is decreasing. This is a negative slope, right? As we go up, we're going down. As we go to the right, we go down. So it makes sense that it's a negative slope. If it's a negative correlation, it's going to be a negative slope. This is just something to keep in mind. All of those things are saying, is my answer reasonable? You're checking as you go along. Yeah, the slope is negative, so I'm doing this correctly. Okay. Now we need to find our b. So our b is the sum of y over n minus m times the sum of x over n. Okay, kind of makes sense. Let's go back to the previous page for a second. So we have b is equal to y hat minus mx, y bar minus mx bar. All we did is we said, okay, let's subtract mx from both sides, okay? So if we subtract mx from both sides, we get b, and we're using y bar and x bar. So The sum of y was 56.7 over 7 minus, you're taking the negative 0.38 times the sum of x, which was 88, over 7. And this gives us 12.88. So now we just plug into our line. Okay, our line is so y hat is equal to negative 0.38x plus 12.88. This is our regression line. Okay, so the next thing that we're going to do is we're going to calculate the residuals, okay? And you're not always going to do this for every x value. We're going to do it for every x value so that you get accustomed to doing it, okay? But you're not always going to do it for every x value. So I'm going to just put this in a chart again. Okay, and it'll put the data on this page. You have your x, then you have your observed y. This is the y that was in your sample. Then you have your y hat. This is your predicted y. This is your negative 0.38x plus 12.88. And finally, you have your residual. Okay. And I'll just put here, these will be your predicted y values. Okay. Remember that your D, this is observed y. Minus the predicted y. Okay. Remember, again, if you're above the line, it's positive. So that could be an easy way to remember that if you're above, it's positive. When your y value for the observed is greater than your y value for the predicted, it's positive. So if you could remember that, then you're not going to mix up the order in which you subtract the residuals, okay? So we're going to do this for every x value. So we're going to do it for the 1, the 10. Again, you're not always going to have to do it for every x. Although I think on your final, in your review sheet, I actually have you do it for every x. But again, that's just to give you practice. Okay. So our observed y's are just coming from the previous table. So these first two rows came from the sample. Okay. This y hat This comes from plugging your x value into the regression line. So what do we get here? This would be negative 0.38 times 1 plus 12.88. And what do we get here? We get 12.5 actually. If we do that for this one, we get 9.08. Remember, use your judgment when rounding, but don't round more than you have to. You're always better off going further, going more decimal places than less, okay? Sorry, I wrote negative 7.8. This is positive. So these we just plug into that equation. That's a 3.76. So now what we do is we subtract the first column and the second and the third column. So we're going to do 12.5 minus 12.5. We get 0. Here we do 8.7 minus 9.08. We get negative 0.38. We do 14.6 minus 10.98. And we get 3.62. We do 5.2 minus 7.18. And we get negative 1.98. 9.9 minus 11.74, negative 1.84. 3.1 minus 3.76, negative 0.66. 2.7 minus 1.48, positive 1.22. So the fact that we see a 0 here says that x equals 1 is actually, the observed value is on the line, negative 0.38x plus 12.88. It is a point that looks like this. It is on the line. The line goes through that point. This says that the observed value, the point from the sample, is below our line of regression. This is a positive 3.62. This is a negative 1.98. Okay, we're below the line of regression. We're below the line of regression. We're below the line of regression. We're above the line of regression. Okay. Okay, so what else can we do here? We can also use the line of regression to predict how much someone will contribute if they have been out of school for 11 years. we could just plug in 11. So y hat is equal to 0.38 times 11, negative 0.38 times 11 plus 12.88. And we get $8,700. So if someone has been out of school for 11 years, which isn't in our sample, okay, so we can't observe how much. If they've been out of school for 11 years, we predict that they're going to contribute $8,700. So that's one of the reasons that we use these regression equations. It's so that we can make these predictions about things that aren't in the data set. If I wanted to know how much somebody will donate if they've been out of school for 20 years. And in that case, we just plug in 20. And we get $5,280,000. Okay, let's do another example. And this one, I'd like you to pause the video and try it on your own, okay? And one of the reasons why I want you to do this is make sure that you're comfortable with the process. And then if you're not, you can go back and rewatch what we did here and watch us go through that example. So in this example, let's look at the height of a building in feet. And the number of stories the building has. That's the same thing as the number of floors. So in this case, the height is the x. The height is the independent or the explanatory variable. And the number of stories is the y. That's the dependent or the response variable. Okay, so the number of stories is going to depend on the height of the building. So let's say we have a height, that's our x, and we have the stories in the building, that's our y. Okay, a building with a height of 1,002 feet has 75 stories. And remember, this is a sample. We're taking a sample and we're doing an analysis of the sample. So we're going to take a sample of the 9 buildings, the 9 tallest buildings in Texas. Okay, so this is actual data. The next building has 992 feet, and that building has 71 stories. The next one is 901 feet tall, and that building has 64 stories. Then we said 780 feet tall, and that building has 56 stories. 762 feet tall, that building has 53 stories. 756 feet tall, that building has 55 stories. 752 feet tall, that building has 48 stories. Then we have 741 feet. That building has 47 stories. And 732 feet. And that building has 53 stories. So these represent the 9 tallest buildings in Texas. So it's just a sample. Okay. So how do we calculate the regression line? Well, we need to calculate the slope and we need to calculate the y-intercept. Okay. Well, in order to calculate the slope and the y-intercept, we need to figure out all of those different sums, just like when we were looking for the correlation coefficient. So it's a tedious process, I understand. So this one, you're taking each of your x values and you're multiplying it by the corresponding y value, the y value that is a response to that x value. So we do 1,002 times 75 plus 992 times 71 plus 901 times 64 plus 780 times 56, 762 times 53 plus 756 times 55 plus 752 times 48 plus 741 times 47 plus 732 times 53. And we get here 438,611. Okay. And it's worth mentioning here that we did not actually find the correlation to show that it was a significant correlation. It is a significant correlation. It's a positive correlation. It kind of makes sense that it would be a positive correlation. Remember, a positive correlation looks like this. I'm going to just make it so that we could see it. Okay. This makes sense that it would be a positive correlation, right? As the number of feet in the building go up, it makes sense that it has more stories, right? So we're not going to test it. I'm going to tell you this correlation is significant. Okay. We then need to calculate the sum of the x values. So we just add all of our x values together. And we get 7,418. We have to do the same thing for our y's. These are the things that we use in the equation. Sum of our y values here is 522. And finally, we need the sum of the squares of our x's. So this is going to be 1002 squared plus 992 squared plus 901 squared plus 780 squared plus 762 squared plus 756 squared plus 752 squared plus 741 squared plus 732 squared. And this gives us 6,210,858. Now we can, so we have our n. Our n is equal to 9. So now we're going to plug in to our slope equation. So again, a reminder, our slope equation is n times the sum of the product of our x, y, minus the sum of x times the sum of our y values over n times the sum of our squares of the x values, and then minus the sum of the x values squared. So this is a plug and chug now. Our n is 9. Our xy is 438,611, right? It's this number up here. Minus 7,418 times 522. And then all of that is over 9 times that last number, 6,210,858. These will typically be very large numbers. Minus 7,418 squared. The top gives us 75,303. And the bottom, when you calculate it, it gives you 870,998. And this gives you a slope of 0.086. So notice positive slope means positive correlation. Your correlation coefficient will be positive. Okay. And we need to find our b. So our b is the sum of our y values over n minus our slope times the sum of the x values over n. So the sum of our y values is 522 over 9 minus 0.086 times 7,418 over 9. And this gives us, weird coincidence, negative 12.88. It's a complete coincidence that that 12.88 is the same. So what is our y hat? 0.086x. That was a weird 8. minus 12.88. Okay, so let's calculate our residuals. And you won't always feel a need to calculate your residuals, okay? We're doing it so that you get some practice. So we have our height. We have the number of stories. So the height is X, the number of stories, Y. Then we have our Y hat, our predicted Y values. This is 0.086X. Minus 12.88. That's the equation that we have to plug into. And then we have the actual residual, which is D. So the first two rows are exactly the same as the first two rows in our table before. It's the same X and Y values, right? So it's 1002, 992, 901. I find it easier to organize as a table, but that is up to you as long as it's very clear what you're doing. It doesn't have to be a table. So that was the first row. Those are all of the different heights of the buildings. Then we have the number of stories in each of those buildings. Always be careful that you're counting and you're making sure that you have the right number of columns. In other words, make sure your n is still 9. Okay, our n was 9 here, so we should have 9 columns, which we do. Okay, so then when we plug in 1002 into our equation, so we're doing 0.086 times 1002 minus 12.88, we get 73.292. So notice I'm rounding to 3 decimal places. Here we get 72.432. Then we get 64.606. Notice the predicted is not all that far from the observed, okay? So here are our observed, the stories, okay? That's what we saw from our sample. The predicted is what happens when we plug it into our equation. It's not that far. Every once in a while you get an outlier where it's really far away, but most of the time it is not that far. Here we get 54.2. That's because it was a 0.200. 52.652. 52.136. 51.792. 50.846. And 50.072. Okay. And our residuals is our observed minus the predicted. Okay. So if it's positive, then our observed is higher. 1.708, negative 1.432. And if we look, our observed is 71 here, and our predicted is over 72. So it makes sense that this would be negative. Negative 0.606, 1.8, 0.348, 2.864, negative 3.792, negative 3.846, and 2.928. Okay, and finally, we can use the regression line to predict the number of stories in a building with that's 900 feet tall. Or we can also do 1,100 feet tall. We can do anything. We wouldn't use it to, let's say, predict the number of stories in a building 100 feet tall, okay? You would use it within so that it's close to the range of the heights. So you probably wouldn't use it for 100 feet, but 950 feet, 1,100 feet, sure. So for 950 feet, that's our x. So we're saying y hat is 0.086 times 950 minus 12.88. And you get 68.2. You would round here, right? You can't have 68.2 stories. So round. So this is the type of thing that you have to think about. In the last example, we didn't have to round. You could contribute $8.7 thousand. Okay, that's absolutely fine. That's $8,700. There's nothing wrong with contributing $8,700. People do it. But here, it is not possible to have 68.2 stories. You don't have to round up. You can just round normally because you actually would not have 69 stories. In fact, in a case like this, you can round either way, okay? But it makes more sense to round down, right? Because you don't have quite enough feet for that extra story. And you have to look at the situation. When we talked about sample sizes, when we were doing confidence intervals, we said always round up, right? That's because if it told you that your sample size should be 132.1 people, you can't have 132.1. But it's also saying 132 is not enough, okay? So you round it up no matter what. Here, you would round down no matter what because it's telling you you don't have enough feet for a 69th story. okay? So, and the same thing would be true if this were 68.8. You don't have enough feet for that last story. So it makes sense to round down in these cases, okay? Let's do 1,100 feet. So all we do is we plug in 1,100. Once we have our equation, we could figure all of this out relatively quickly. It's the huge advantage of having that equation. So in this building, we have enough for 81 stories. Okay. And that explanation for the other 0.72, it could just be, you know, these lines aren't perfect. You're going with the best fit line. It could be that that extra distance that you have, that extra 0.72 of a foot, okay, maybe it's just added on one of the ceilings is a little thicker, okay, but you don't have enough for not that 0.72 feet, that 0.72 story, okay, maybe the ceilings are thicker throughout because they have that extra room. So I wouldn't read too much into the fact that that's 81.72. Remember, these are all approximations, okay? All of these are approximations. It's never going to be exact. You're using what you did in a sample to approximate the population. This is the same thing that we've been doing all the time, right? We used this sample to help us make predictions about the population. It's never exactly the same, okay? It's a best fit line only. It's not perfect. It's not exact. Okay. And that's it for correlation, actually for all of correlation and linear regression. The next two lectures, which will be the last two lectures, are on chi-square regression. So it's a little bit different. It's still working with two variables, but it's working with them in very different ways. It's going back to frequency distributions. Okay. And that is it for this lecture.